I am. Everyone all set? Okay. So, good afternoon, everyone. Thank you for coming today to our Capstone 2 final project presentation. My name is John Bell, and I'm here with Andrew Cote, Kelsey Bern, Brendan Cavers, and Aodhan Dougherty. So, on today's agenda, we will first introduce the project scope. Then, we'll go over any background knowledge needed to understand the project. We will then discuss what we completed for the project, and then finally, we'll give our conclusion and open the door for your questions. So, for our project, we competed in the Department of Energy Tech Up competition. This competition required teams to develop a business plan which leveraged a national laboratory developed technology. These business plans, once completed, were then presented in front of a panel of judges at a regional competition event. We chose to focus on pink hydrogen and how we could bring it to market. In order to successfully compete in the competition, we had to work together and manage our time effectively. To do this, we met multiple times throughout the week and had group work sessions, while always being in constant contact through group chats and Microsoft Teams. So, as a team, we had 6 main goals. The first of those goals was to compete in the Department of Energy's Tech Up competition and to place in the top 20%. Our second goal was to develop a sustainable and profitable business plan for the production and distribution of pink hydrogen. Next was to connect with experts to seek insight into the nuclear pink hydrogen industry to ensure successful implementation of our business plan and technology. Next was to conduct thorough market research to identify potential customers, market trends, and competitors in the pink hydrogen industry. Next was to develop a comprehensive financial plan that demonstrates the economic feasibility and profitability of our business plan. And lastly was to complete all Capstone deliverables on time. Now I'd like to welcome Kelsey Bern, who's going to talk about the outside resources that we use to help develop our business plan.
Thank you, John. Hi, everyone. As John said, I'm going to discuss the outside resources we used and the work we completed for our competition. Our team relied heavily on our outside resources. We chose pink hydrogen with minimal knowledge to begin with, but we chose it because we wanted to learn more and we wanted to challenge ourselves. And a challenge we got. In the first couple weeks when we started to deep dive into our competition, we quickly realized we were in way over our heads and we're going to need a lot of industry experts to get this done. That's when Andrew Cote reached out to MMA's president, Jerry Paul, and asked him to put us in contact with his pink hydrogen contacts. We got very lucky and we were able to speak with John Austin, Bill Waberson, and Dr. Cross. My bad. All 3 of them helped us gain a better understanding of the information we needed to compete. I do want to highlight John Austin with Excel because he was able to give us the figures that we needed to complete our economic feasibility, and this was a major component to be able to compete in the competition. The last person we met with was Lynette Casey. Unfortunately, we were not able to speak with her prior to our competition, but she was able to give us insight on how retrofitting nuclear plants with new steam turbines would tip the scales even more in favor of pink hydrogen. While she was not helpful for our competition, it will be for next year's. As part of kind of everything that we did for our Capstone project, we created what we call a Tech Up Tips document, which will be passed along to next year's Capstone seniors. And in this document, we listed everything we completed for this competition, everything we learned, and all the information that was given to us by our outside resources. From the information given by our outside resources, we were able to complete the deliverables for the competition. The Tech Up competition was broken up into 4 parts. First, the entrance phase, then explore, refine, and pitch. For the entrance phase, our team submitted a 200-word written summary which explained what pink hydrogen was and how it could aid in the energy transition. In this summary, we explained that pink hydrogen is the practice of using excess nuclear energy during low load demand times to power electrolysis cells that then produce hydrogen. The summary also elaborated on how nuclear facilities could run at maximum capacity year-round, which would increase their longevity and efficiency. Lastly, it explained how the implementation of pink hydrogen would lower overall emissions. The 200-word summary met the judge's requirement and allowed us entry into the explore phase of the competition. As part of the explore phase, we created a 7-minute presentation which we presented to a panel of judges at the Northeast Regional Explore event. We were up against some pretty big competition, including Cornell, UMaine, and a lot of pretty heavy-hitting schools. But for this presentation, we were asked to include several sections. The first was the technology identification, which we described what pink hydrogen was. The next was a current market analysis, which explained how pink hydrogen has the potential to create a new sector in the market. Currently, 95% of hydrogen is produced through emissions-producing methods, and this leaves an opportunity for pink hydrogen to make a huge impact on emissions reduction. The next important section was explaining who would buy the technology. We started off by saying that nuclear plants would buy the electrolysis cells to produce the hydrogen, and from there they could sell the hydrogen to what we referred to as hydrogen hubs. Hydrogen hubs are the co-location of several industries, including power generation industry, transportation industry, petroleum refinery, and ammonia generation facilities. The next section we included was the potential impact that pink hydrogen could have on the energy transition. In this section, we highlighted that hydrogen, when it's burned as a fuel source, produces 0 emissions. All it produces is water. This means that if we can produce hydrogen from minimally emissions-producing methods, such as nuclear, we are taking a step in the right direction to decarbonize our grid and potentially the world. We were also asked to include how we would define the success of pink hydrogen. In this section, we noted the key steps would be first, proof of concept, next, developing a hydrogen infrastructure, third, the utilization of hydrogen in industry, and lastly, reduction of emissions as a result of the use of pink hydrogen. So that is an overview of the people who helped us along the way and part of what we completed for the competition. Next, we have my teammate Andrew Cote, who will be discussing the last section that we completed for the explore phase, which will be the economic feasibility of pink hydrogen.
Thank you for that introduction, Kelsey. As a team, we need to consider the cost of implementing an electrolysis system to determine the economic feasibility of pink hydrogen. This involved calculating the potential cost a business might incur to make use of this technology. With the documentation provided by John Austin, we were able to complete an economic feasibility analysis for the installation and operation of a 100 megawatt high temperature steam electrolysis system, or HTSE. From our analysis, we projected that the 100 megawatt system could produce 23.4 million kilograms of hydrogen per year, or 64 metric tons per day, which at a sale of $2.50 per kilogram would generate an annual revenue of $58.5 million. We also considered the additional revenues from the implementation of carbon credits, which were determined by calculating the amount of CO2 emissions avoided from producing hydrogen from the HTSE method rather than the conventional steam methane reforming method. We found that 213.7 million kilograms of CO2 would be avoided by utilizing HTSE. Our analysis showed that carbon credits would generate a high and low carbon credit revenue of $5.3 and $21.3 million. This is based on a relatively conservative low carbon credit of $25 per ton of CO2 avoided and an optimistic high carbon credit of $100 per ton of CO2 avoided. Taking into account the revenue and costs, we projected an annual profit of $9.3 million, which could increase to $14.7 and $30.7 million with low and high carbon credits. We also determined that the break-even point for this project is about 13 years without carbon credits, but can be accelerated to 8 or 4 years with low and high carbon credits, as shown by the graph. Based on these findings, we concluded that the investment in the HTSE system for pink hydrogen production is economically feasible, and implementation of carbon credits will further incentivize the production of clean energy. This reiterates the importance of the implementation of carbon credit for the prosperity of pink hydrogen and other clean energies. To summarize, our economic feasibility analysis showed that pink hydrogen through a 100 megawatt HTSE system presents a promising investment opportunity. Our project not only projects to produce a significant amount of hydrogen per day, but also contributes to mitigating the effects of climate change by avoiding CO2 emissions. We emphasize that the inclusion of carbon credits will incentivize the project and has the potential to generate even higher revenues. It's important to note that these numbers only reflect the sale of hydrogen per kilogram and do not account for the possible profits from power purchase agreements with significant hydrogen consumers. Long-term contracts could result in additional revenues, generating more profits from various industries and byproduct applications. Overall, this project is a step towards a cleaner and more sustainable future. Knowing our project was economically feasible, we could confidently present it to the Tech Up judges and determine the strength of our business plan. So next, we have Brandon Cavers, who will be discussing the results and tips from participating in the competition.
All right, thank you, Andy, for the intro. And like he mentioned, I will be discussing the results and the tips. As you can see here, we have 3 result topics. First, our 200-word essay was accepted on February 6th, which gained us an entrance into the competition. This was our biggest step. On February 16th, our team competed in the Northeast Regional Competition, and our result was losing the regional prize to Carbon to Stone from Cornell University. At the end of the competition, we have found out that we were entered into a bonus prize for nuclear. After all regional events were complete, there was a total of 3 teams in the nuclear bonus prize sector. We lost the bonus prize to additively manufactured sensors for nuclear by Boise State. Although we didn't win, we gained experience with this competition, which we would like to share with future MMA teams. Here are the tips we generated for next year's students. The thing that caused us to struggle the most was the amount of time we had to gather info and produce a presentation. We had about 2 weeks, which was very tight for us. We recommend that you start this project early, finish the 200-word essay first, and immediately after start your presentation. Using school resources will be very helpful. There is a lot of faculty here who have contacts in the industry, and along with using school resources, it may be helpful to use our same topic. Using our topic will help level the playing field since the competition you're against have many years of construction. Another way to help win money would be to pick a topic that would stand alone. This will allow you to win a bonus prize by default. Next up is Aodhan, and he will be talking about our lessons learned and to conclude our presentation.
Thank you, Brendan. As Brendan mentioned, I will discuss the lessons learned and the conclusion of the project. These are the lessons that we learned while completing this project. The first lesson we learned was to ensure that your group communicates amongst themselves regularly. Intergroup communication is key and essential to making sure that your submittals are turned in on time and group morale is high within the group. Communication with Professor Ferreira is also key to guaranteeing that submittals are up to the proper grading standard. The next lesson we learned was to set a schedule. When you have a properly formatted schedule, it is much easier to see the team's progress and ensure that you are on schedule as a group. If you are out of sequence in the schedule, granted that it's formatted properly, it should reflect that. This makes it super easy to track time management. Our next tip and kind of lesson to learn was to remember the 5 Ps. Proper preparation prevents poor performance. If you prepare properly, you'll perform accordingly. Another lesson learned was to schedule more meetings than required. As a group, we met multiple times a week, whether it was in person or over Microsoft Teams. This helped the team drastically with time management and staying ahead of the due dates for the project. We also met as a team for group work sessions. This made it easier to make sure that all of the deliverables were aligned before the final alignment meeting with Professor Sadie Ali Ferreira. The last lesson learned was to schedule that weekly alignment meeting with the professor to ensure that the deliverables are in alignment with each other and to mitigate point deductions. In conclusion, we competed in the Department of Energy Tech Up competition. This competition required teams to develop a business plan which leveraged a national laboratory-developed technology. Our business plan focused on pink hydrogen and the economic feasibility of bringing that to market. Our business plan was presented at the Northeast Regional Competition where we were nominated for the Nuclear Technology Bonus Prize, which was a chance to win $25,000. We lost in the final round to Boise State. This project was a fun opportunity to work with your peers and fully understand all the processes that a group project and presentation entail. The DOE Tech Up competition proved that with a team of committed individuals, Maine Maritime Academy can compete with other prestigious institutions. Thank you. This concludes our presentation. Now we'll open the floor to any questions that you may have about our project.
You didn't show the bad photo, which is good. Yes, Professor. Uh-oh. Smart move.
Hello?
Yep, now it's working.
All right. My question was, what sources did you use to figure out the installation and operational costs?
So from the Excel document, they had a techno-economical analysis for their plants in Monticello and Prairie Islands that they're going to be installing there. It's like a 600 megawatt plant and like a 400 megawatt plant. And they've done a lot of research into the capital installation costs and operational costs. So what I did was I took those figures and scaled it down about 15%. I made sure both were relatively the same scale, just to ensure the numbers would match. So basically it was just scaled based off of those numbers, so it was able to convert over relatively well.
Cool, that's interesting.
Nice job on your presentation. Thank you. For those who didn't get a chance to watch your presentation in the competition, can you talk just a little bit about some of the other schools and what they presented? You did talk a little bit about stiff competition, and I think that the rest of the class could really benefit from hearing a little bit about your competition.
So a lot of the other teams in the competitions, while I can't remember 100% what their topics were and everything, a lot of what they talked about and a lot of the big thing was carbon reduction and carbon emissions this year. We went up against teams like Harvard, Cornell, and a lot of the Ivy League schools. A lot of these teams and the programs that they were implementing into this competition were projects that they've been working on for doctorates or as a group for, they were kind of sourcing funding and stuff like that, looking for crowdsourced funding so they could actually get their projects up off the floor and kind of running. So that's kind of where we ran into, we did it in 2 weeks. And it was a lot to do in 2 weeks. But other than that, we did go against a lot of Ivy League schools that had a lot more resources and funding than Maine Maritime has, but we still made it into the final group for the Nuclear Bonus Prize, which is good.
Could you talk more about the electrolysis you mentioned earlier in the presentation? Like, how is that different than other forms of electrolysis?
Yeah, so the HTSC system, it's basically the same principle as the modern electrolysis units, like the polymer electrolysis membranes and stuff like that. But rather than having an expensive catalyst to accelerate the production of hydrogen, it utilizes the high temperature steam from the light water reactor, just utilizing process steam from the nuclear power plant to increase its thermal efficiency, so it can produce more and accelerate production that way, rather than, and it also saves on electricity, so because you don't have to heat up that water before using it in the electrolysis. So it's more efficiency, less cost. So it helps in both aspects.
First of all, thank you guys very much for presenting that all that information to us. It was very interesting to learn about. My question is, in your many different analyses that you completed for the feasibility of this kind of technology, did you come across any kind of specific criteria that a nuclear power plant would want to meet for implementing this sort of technology in their plant, or is this technology like very universal and able to be implemented in almost any nuclear plant?
I think the most of it would be to be competitive with SMRs, because you don't want to be paying more for a technology to produce hydrogen than if it's going to cost you more to make it than to if it's going to cost you more to make it through HCSE rather than. Do you have anything to that?
A big part of that was also making sure that the nuclear plants that you implement it as have space to have that hydrogen hub, because it's not economically feasible to transport hydrogen unless it's in a pipeline. And so making sure that the nuclear sites you implement it at have the proper permitting, and then on top of that, the space to have that hydrogen hub was a really important piece.
So I think my question is very kind of similar, but is this pink hydrogen supposed to be formed at like a traditional, like already installed nuclear power plant, not a new, like purpose-built one?
Preferably, the best opportunity to do this would be when plants are upgrading. Like when we spoke with Lynette Casey, she was talking about how when nuclear facilities are upgrading their steam turbines would be a great opportunity to implement the extra hydrogen facility. So they could, because they would already be upgrading the facility. So that is where we're aiming for.
Nice, awesome.
Did you identify any specific nuclear plant that could be a good fit?
There were a couple. Obviously, the Monticello and Prairie Island plants, they're heavily investing into this. And do you remember the other ones that you
So a lot of what we ran into too, especially with talking to nuclear plants, was confidentiality. So a lot of these plants are already looking at implementing pink hydrogen into their system. There's the Palo Verde plant in Arizona now that's starting that up as well. I think Lynette is kind of heading that with Siemens, not 100%. But that's one of the main things that we ran into was confidentiality. So talking to nuclear plants and trying to reach out to plants and getting information back from them, they didn't want to do that because we don't have clearance. But what we found was a lot of the electrolyzers that we've looked into, I think there was one from NREL Energy. It's already a modulated electrolyzer. So it's pretty much just you bring your hydrogen skid into your plant and link it up, and it should be okay. Obviously, there's kinks to work out when you do that, as with everything. But that's kind of what we figured out.
All right, so I just have a question about all of this. So with it being so, economically friendly, and the idea and the aggressive push towards lessening carbon emissions and emissions in general, how far away are we from fully utilizing this? Do you personally think through your research?
Yeah, so government funding is going to be a big part of this. A lot of kind of what we ran into and what Lynette talked to us about and what John Austin talked to us about was, once you've created this hydrogen, what are you going to do with it? Hydrogen storage is a big issue in the country and everything because hydrogen molecules can go through steel. So pipelines would have to be retrofitted, either current pipelines, you'd have to stainless steel sleeve them or create all new stainless steel pipelines. Or you can use ammonia as a carrier and then fracture off that hydrogen with an ammonia splitter. I think we kind of concluded that this will be coming up in the next 10 to 15 years, and it will have that big boom in the industry. But a lot of it is kind of hush-hush right now. We don't have the infrastructure for pipelines of hydrogen, and that's the biggest thing, and is how to store and transport it that we ran into. That was the biggest problem.
A lot of the companies that we talked to too said they're still in their infant stages. They're still like proof of concept testing to make sure that all of this makes sense. And so when we were talking with Excel and the plants that they're working to implement it as, it's still really small scale to make sure that it makes sense and is economically viable to do it in the first place.
Thank you.
Did you guys include the distribution costs of the hydrogen in your final calculations, or just the generating costs?
No, it was just the cost to generate it. It wasn't including any of the distribution, but our ideal goal is that having them all in a hub, you wouldn't really have to transport it at all. So if you have all kinds of byproduct plants nearby, then you can just pipe it directly to them and minimize your transportation costs.
Okay, thank you.
Anything else? Okay. Well, thank you guys for coming out. Have a good day.